Are you considering breeding ball pythons, but you're just trying to wrap your head around all the different genes that these beautiful creatures can have? Or did you just go on a Facebook group and ask if your brand new normal ball python is in fact a normal, and half the people said, yeah, and the other half said, no way, and now you're confused? Well, let's try to demystify things. We're going to talk about genetics today, but we're going to keep it simple, and we're going to keep it interesting, and we're going to look at some snakes. Welcome to the Python Green Room. I'm Bob Bledsoe. This is Lydia Dietz. Lydia is a ball python who is just a baby, and she is heterozygous for the recessive gene pied and homozygous for the recessive gene clown, and we're going to talk about exactly what that means. Behind the camera, as always, is my brother Kent. Hi. Kent, I think, is getting over his fear of snakes. No, I am not. Okay. So when we talk about genes in ball pythons, we're talking about genetics that alter the color and pattern, mostly, of the snake. And there are 4 different types of these genes that we're going to cover. And in each case, some people get this a little bit confused, but in each case, there are 2 potential copies of that gene. Hi folks, Future Bob here, just editing videos for Past Bob and clearing up confusing information. The 2 potential genes that Past Bob is talking about means that on the chromosome there are 2 spots for genes. There's always going to be 2 genes there. It could be a normal and a morph, or it could be 2 morphs. That's what we're going to talk about. For those of you that are genetic experts, we're not going to get into allelic genes today because that confuses things. Also, as many of you know who have seen my other videos, in the future we wear real cool hats. The snake gets 1 copy from the dad and 1 copy of the mom in every case. And these are the types that we're talking about: recessive, dominant, codominant, and incomplete dominant. In a recessive gene, let's talk about recessive first, since I have a recessive gene snake in my hand right now. And we're also going to talk about this in terms of the snakes that I have, but also we're going to use a hypothetical fake gene in a hypothetical snake. Look at my hypothetical snake. That's a normal right there. Normal snake. We're going to use 1 gene, and this gene colors the snake green. There's no such thing as that in ball python. Man, I wish there was. Wouldn't it be cool to have a green, bright green ball python? But in this scenario, this is a gene that makes the snake green, and we're going to talk about what it does if it were recessive, dominant, codominant, or incomplete dominant, and how that works, because based on whether the snake has 1 copy of the gene or 2 copies of the gene, that's going to do different things in all 4 of those different types of genes. So let's talk about recessive right now. In a recessive snake, let's do this. I've got these little pieces of tape that I've cut, and we're going to say that this is a chromosome, and the mother is going to give genes. I don't know how accurate this is, but it's close enough for understanding how this works. I know that it works like this. I don't think a chromosome looks like a door to a closet, but we're going to say that is the gene from the mother. Now, the mother has an option where this is the location for the green gene. Okay, the green gene is located right here on this chromosome that goes up and down. Right here is where the green gene could potentially go. And in this case, the snake can either have a green gene or a normal gene. And what's happened here is mom gave a normal gene to the snake. Dad gave a green gene. He only has 1 copy of the green gene at this point. And he looks like this because he only has 1 copy of the green gene. So in other words, in a recessive snake, in a recessive gene, 1 copy shows nothing. They can have the gene, but you can't tell visually that they have it. Lydia Dietz is a great example of that because she has 1 copy of the pied gene, and she doesn't look anything like a pied. If she had 2 copies, she would look more like Lucille. Lucille is a pied. She has 2 copies of the pied gene, and that's why she looks like this. Now, what Lydia Dietz does have 2 copies of is the clown gene. And clown is such a cool looking pattern, and color morph too, but the pattern is so striking with clown. So she has 2 copies. So she is a visual clown, and she is het for pied. The only reason that we know she's het for pied is that one of her parents was a visual pied. So we know that that visual pied had 2 copies of the gene, and so the only option is to give 1 copy to the offspring. They didn't have the option of giving a normal to the offspring. So we know that she's het for pied because of that. In the case of 1 copy of the green gene, snake looks normal. 2 copies of the green gene, let's say that mom gives a copy of the green gene. Now, in a recessive snake, now there's no other gene at that location in the chromosome to show, recessive means that it's going to be recessive to some other gene that's in that's in that location of the chromosome, and that's why that snake looked normal, because it was the normal gene showing from the mom, and green is the recessive gene. So now that there's no other option, bam, green gene. That's recessive genes. So remember, whether it's dominant, recessive, codominant, or incomplete dominant, you have the possibility of having 1 copy of the gene or 2 copies of the gene. 1 copy is a het, or heterozygous. 2 copies is homozygous. What confuses people sometimes is when they're talking about what we call codominant genes. A pastel, for example. 1 copy of the gene, we call that a pastel. 2 copies of the gene, we call it a super pastel. That's very common with a lot of these codom genes in ball pythons, as we call one the name of the gene and then the other one same name but super in front of it. It's still a pastel is technically a het pastel because they have 1 copy of the gene. We just don't say that in the ball python world. So the inspector is banana. He has 1 copy of the banana gene. Technically, he is het banana. I mean, this is nitpicky, but Bob did misspeak. It would actually be het for super pastel or het for super banana. The snake would be het for whatever the double gene combo is named. And if you're enjoying this video, by the way, or you're getting something out of it, hit the like button. The subscribe button would be great. Leave a comment. This is a brand new channel, so any of those things would really help us out. Now let's talk about dominant genes. This is Damara. She is a pinstripe and a delightful snake. Love her so much. She's a big girl. She's 3,400 grams. She's a pinstripe, and pinstripe is a dominant gene. So with a dominant gene, let's say that you have 1 copy of a normal and 1 copy of a green gene. Now remember how recessive was going to be recessive to any other gene that's in that spot? Dominant is the opposite. It's going to be dominant to any other gene in that spot. So it's just going to show a green snake. That's dominant. If there were 2 copies of that gene, same snake, same thing. So with Damara, I don't know if she has 1 copy or 2 copies of the pinstripe gene, because either way, I'm going to get a little closer so you can see her patterning. Either way, her color and pattern are going to look like this. I want to talk about the difference between incomplete dominant and codominant, because there's a mix-up in the ball python community. We refer to a lot of different genes as codom. I don't think we don't really, in general, refer to anything as incomplete dominant unless it's somebody who's trying to speak accurately about it. And I like to speak accurately about it, but I also don't want to cause confusion. So here's my point. For an actual scientific codominant gene, if we have 1 copy of normal, let's say from the mom, and 1 copy of the green gene from the dad, the gender doesn't matter whether it's mom or dad or whatever, but just one gives a normal, 1 gives a green. The snake will look like this. Patches of green, patches of brown. It's like a calico cat. It's like I don't even know what they're called, but there's some livestock that are codom, where cows with different patches of like red hair and things like that, and chickens with some black feathers, some white feathers. Instead of just combining together and making gray, they have actual patches. So that is scientifically what a codominant gene is. And then, you know, when you have two copies like that, then we get ba-bam, green snake. Let's talk about what incomplete dominant does. An incomplete dominant snake, where is it? There it is. If there was one copy of each, I got my hands full now, so I'm not going to change it, but if there was a normal and then a green, that's what it would look like. Combination of normal and green would be the single gene form. And that's what most of these snakes have. It's actually incomplete dominant. We generally refer to it as codom. And then when you have two of those genes, you might get a green snake, or you might get this, which would be considered a leucistic snake. And there's a lot of genes, or a handful of genes, that do something really cool to the pattern or color of the snake. And then when you get two copies of those, you end up with a completely white snake with either blue eyes or black eyes, depending on what the gene is. So let's talk about the inspector, because he's real interesting. He has a number of genes that we know he has, and then he's got some potentials that we're just kind of guessing on at this point. So he's banana, which is the most visually dominant gene that he has, and it's also masking some of the other potentials. And banana is what we're calling a codom gene, and he's got one copy of that gene. He's also inchy, and both his parents were inchy. So he could be super inchy, and I believe he probably is. I think he's going to prove out to be that, but it's hard to tell because he's also orange dream. So inchy is what causes the banding on the pattern, this reduction of the pattern. Inchy does that. Super inchy does it even more, and he has pretty reduced banding, but orange dream also reduces the banding, and both of his parents were orange dream, so he could be a super. Here's how we know if he is super inchy or super orange dream. If all of his babies come out inchy or all of them come out orange dream, we know that we either hit really incredible odds or he's a super, because that means that he only if he's a super, let's say he's super inchy, that means he has two copies of the inchy gene, and his only option is to pass that gene on to his babies. One of his parents was also fire and pastel. So he could have fire in him, he could have pastel. Those are pretty subtle genes when we're also dealing with banana and such a light snake like this. So it's really hard to tell if he actually has fire or pastel. But we'll be able to tell if he has some babies that are fire and pastel. Now, here's the strategy with proving him out. Usually, when you're talking about proving out a snake like this, you're not quite sure the genes. The best thing to do is pair them with a normal, because you know that normal is going to throw just normal looking snakes, and any additional visual genes are going to be from the snake that you're trying to prove out. So I don't have any normals to pair him with, but I do have Lucille, who's the pied. And Lucille is only pied. She doesn't have any other genes. She has two copies of the pied gene. So she has to give one copy. It's her only option. But remember, pied is a recessive gene. So any baby that only has one copy of the gene isn't going to show pied at all. The only thing they're going to show is the genes that he has. He doesn't have pied, so he can't give a copy of a pied gene. So what will happen is with that particular pairing, the inspector to Lucille, is that every baby will get one of Lucille's pied genes. Anything, and so obviously they're not going to show pied. Anything that they show visually as far as other genetics will have come from him. So that's how we prove him out. These, by the way, were done by a kindergarten class here in Burbank, California. No? And wait a second, I watched you color those. Okay, I was joking. I did do them, but I did them really fast. I didn't have any time, so I had a lot of stuff going on, so I just whipped them out in like 15 minutes. No, it took you like half the day, don't you remember? Kent, yeah. Could you... It's hard for me to think about genetics when you're talking. Oh yeah, sorry. All the time, so if you could just... No problem. Thank you. I just didn't know if you forgot that it took you half the day to color the children's coloring. Let's talk about one more genetic thing that confuses people sometimes, and we will use Molly Malone for this case because it applies to her. Molly Malone has 3 recessive genes that are in play. The only one that shows up is ultramel. She is a homozygous ultramel ball python, and that is the reason for this crazy patterning down her dorsal and her coloring of orange and caramel colors. Just a beautiful snake. She is heterozygous for pied, 100% het pied. What that means is we know for sure she's 100% het pied. The reason we know that is that one of her parents was a visual pied, meaning that parent had 2 copies of the pied gene. Their only option is to give one of those copies to the baby. Every baby that parent has will have at least 1 copy of a pied gene. So we know she's 100% het pied. She's also 50% het hypo. What that means is the hypo gene, which kind of makes a snake look like they're in shed all the time. It's also called ghost. But what that means that she's 50% het hypo is that one of her parents was het hypo. So one of her parents had a hypo gene and a normal gene. There's a 50% chance that they could have given the normal, and there's a 50% chance that they could have given the hypo gene. So what that means, she either is hypo or she is not hypo. She's either, in reality, 100% or 0%. However, we don't know, so we're saying there's a 50% chance of it. And I would have to prove, I would have to breed her when she gets older and prove that out, that she's hypo. So we know she's ultramel because we can see it. We know she's got 1 copy of the pied gene because of her parents. And we know, I'm real sorry about this. He's just trying to hold the snake. I don't think he means anything by it. You know what? I'll fix it. That there's a possibility, 50% possibility, that she has 1 copy of the hypo gene because we know that one of her parents was for sure het hypo. Now let's talk about this situation that happens all the time in the Facebook groups. Somebody gets a new normal snake, or they buy it as a normal, and they put a picture up on it and they say, I just bought this as a normal, but it seems light and I'm pretty sure it's something else. What is it? And then you get half the people saying, it's definitely normal, it's nothing else. And the other half going, I don't know, man, it looks like my snake. Mine's a fire and it kind of looks like mine. And it doesn't have the alien heads aren't big enough on it for it to be a normal. It's got to be something else. So here's something that's really important to understand. The genes that we've identified and named are only genes that have a significant enough visual presence for us to go, wow, that's something that I want to reproduce. That's something that I want to see if it's inheritable, and if so, we're going to call it a gene and we're going to reproduce that. There are thousands and thousands of genes that do different things visually to a snake. So when we say that's a normal, a lot of people say that's a normal morph. There's no normal morph. It's not like that's one morph. A normal is just a snake that looks like a wild type snake that doesn't appear to have any genes present that we have identified and named. But that snake has thousands of genes that are all working to make that snake look like it looks. So normal ball python in the wild could be really dark or really light, or have perfect alien heads along its side, or have really reduced alien heads along its side. Just because they've got all these other genes that we haven't really identified and named because we either haven't found them or we're not interested. It's such a subtle thing that it doesn't matter, So that's why there's such a huge variation of normal ball pythons. I see a lot of people post pictures of their two normals and they look totally different, and they're like, which one is a gene, which one? Well, it's all genes, it's all genetics. But that doesn't mean that either one of those normals necessarily has a gene that we have particularly identified. I hope that makes sense. We're at the end of this genetics video, but I thought that I would show one more snake for the closing. This is Freya. She was featured in our last video, breeding with the inspector. And Freya is the dominant gene calico, and she's a really great expression of calico. She's that's the white that goes up her side like that. It's also called sugar, and a lot of times it's a lot more faint than this, and it's a lot more speckling, but she's a lovely calico. She is the codom gene, which is actually incomplete dominant, orange dream, and also extreme gene. We're going to find out what extreme gene does to the babies, because I'm not too familiar with that gene, but I'm excited about it. And I'm also excited about potentially making some super orange dreams, because she could give one copy of orange dream to her babies, and the inspector can give one copy of orange dream to the babies. So one copy from her, one copy from him, makes a super orange dream, which is a beautiful snake. So some of those babies could be supers. I think we have a 25% chance of that. That may be correct. If not, I'm sure that future Bob will jump on and say something. No, he's actually right this time. Anyway, thanks for joining me in this video. Kent, do you have any questions?
Was not listening.
Okay, fantastic. Thanks, everybody. I'll see you next time.
You didn't tell him to like and subscribe.
I'll do it.
Like and subscribe. Smash that subscribe.